Matteo. Thank you. And we can move on to HYScale again with the presentation of the highlights and key results of the project.
My name is Tobias Moritz. I'm a scientist at the German Aerospace Center. And yeah, the results I will show here are also from Jagoda, who did the internal design of the set, and Wendelin mostly did the stack development. So, but why is German Aerospace Center doing also this energy research? So we're not a research institution and a space agency. We also do research for aeronautics, space, but also transport and energy applications. We have like 30 sites across Germany, and yeah, my institute is in Stuttgart. And there at the electrochemical energy technology, we're doing experimental work like random diagnostic, quality control, validation, performance, and also modeling. And all this for electrolysis, fuel cells, and batteries. And applications can be then energy transport, but also fuel cells for aeronautics or space applications. The agenda of the selected results is shown here. So first, I will discuss a stack PDL design with a flexible element, then the stack and test bench design, and a third point, the analysis of environmental catalyst layers, which is also a point where we can collaborate. So if you have samples that are interesting and there will be a publication that could come out of that, yeah, I would be happy to discuss it. Okay, first point, the stack PDL design is a flexible element. So on A, there is the standard design shown, let's say like this, with the flow field, we have a PDL, then the membrane, carbon paper on the other side, and also flow field and membrane again. Our proposed design is now shown on the right side. So we have a stack design of 3 elements, like expanded field and between PDL with knitted. So that means it's a flexible element, and then on top the standard PDL with liquid fat. In the middle, then the membrane, and then again carbon paper, and the flow field on the other side if needed, or also no flow field on the other side. What does this mean now for performance? So here you see on the right side the performance curve of the setup with the knitted mesh or without the knitted mesh, and it's clearly visible that we can increase the performance quite a lot when we use that knitted mesh. But now on the next slides, we want to discuss why is it like that. So for the structural characterization, here SEM images are shown on A, and you see that you cannot see anything too much because the fibers are just too big. Only thing you maybe can see on knitted mesh 4 on the right side that you can see already through the structure. That means the porosity is so high that also on the curves on B, we can see that the tortuosity goes close to 1. That means we have read-through passes through the material. And the relative diffusivity increases as the porosity increases. This is clear. So we had 4 different ones with nickel and also 4 different knitted meshes with inconel. As we tried this also as more corrosion resistant material. On D, there's the result of a simulation shown where we did capillary pressure curves, and the oxygen saturation of the different knitted meshes is shown at 500 Pascal pressure and 1000 Pascal pressure, and it's clearly visible that the materials with the higher porosity have much faster higher oxygen saturation. Then we did a Fujifilm pressure sensitive film imaging. That means you stack the materials, and instead of the membrane, we have the Fujifilm in the middle. And on A, we had not the knitted mesh, and on B, we had the knitted mesh. And it's clearly visible that the expanded mesh is still visible on the Fujifilm on A, but not on B. So that means that the pressure distribution is much better with that flexible element. And here below, there's also one of these nickel fiber visible. And this is quite nice with that geodetic software. So we can really see the single fibers. There's like a fiber AI where these single fibers can be followed, and also, let's say, after operation, if something changed. For contact resistance, it's shown on the right side, and these are quite low. So in milliohm per square centimeter, in blue, it's visible the clamping pressure that is typical for a stack. So the contact resistance between the stack materials is quite low. So we are not planning to really combine them because this would be a problem then for flexible element. But for stacking, sure, it's more complicated to have them separated. And now the performance curves between these different knitted meshes. Without knitted mesh, there's the lowest performance, like shown here in black and purple. And the highest performance is for the intermediate porosity knitted meshes. That means there is a balance between the heat transfer, electronic conductivity, and then also the porosity. And knitted meshes 2 and 3 show here the highest performance. And this will also be seen that here on the clean spectroscopy. Then on this image, it showed the porosity, how it changes when it's compressed. So because it's flexible, it will also get compressed, and that means that the porosity is a little bit reduced when compressed and in the stack. And this inconel, the material is more has a higher stiffness. That means also that the compression is lower, but the spring is also less, so it's less flexible. We upscaled it here. It's a pad with 15 centimeters diameter, but also we have also square ones with 20 by 20. And now the question is if the PDL on top has large influence still or not when we have the flexible element, because it evens out the pressure distribution. And here on these measurements, we have a lot of different PTLs on top of that knitted mesh. And when we use that knitted mesh, the high pressure points are reduced by around 50%. So this is here, the pressure in megapascal is shown the high pressure points with knitted mesh, and here without, so we have these at a higher amount. And the greatest pressure improvement but was still with the PDL form backup with 2 porosities. So our stacked components in the end have like an expanded mesh, very high porosity. Then we have the knitted mesh, and then still we have a PDL with 2 porosities because the porosity on top is quite low that the chemistry layer can be apart much better. And when comparing all these PDL then on top with one knitted mesh, we see that the performance is quite similar. So that means when we use the expanded mesh, in addition, the choice of PDL on top is not so important anymore. And that means that can be also used the cost-effective one. Still, the backup one was the best, but also cheaper ones would be better. Then for the second test bench design, so like Daniel already have shown, the membrane was upscaled to 30 by 30 centimeters. We will use 20 by 20 for the stack. And it has comparable performance to a smaller scale. And this membrane had different optimization steps for the membrane, but also for the catalyst layer, increase performance and reducing hydrogen crossover. And I have to mention that the PDL comes from Backward, and this has been upscaled to really industrial scale. The membrane from Zenmark is upscaled, and also the catalyst, and now to our stack. So this is like a model of the stack and the design. It has 100 kilowatt in the end with 70 cells. And the active area is 20 by 20 square centimeter. And you can see here from outside that the tyrants, for example, go in the stack. And for the electrical connections, we decided in the end not like here. We have here the produced short stack. We have 5 connectors. Because it would be heat generation at 1 kV would be too much divided in 5. And also the current distribution is better in that orientation. Okay. Then our test bench, it's shown here. It works up to 1000 amps, 30 volts, and 10 liters per minute. But what we are really proud of is that we are really close to zero stainless steel in our test bench. So we have coated with silicon carbide. We have found some nice tubes also that can hold up a pressure up to 15 bar or even higher. And with that design, we can use dry and wet cathode. And we developed here our own lab sheet software that can be used then for automatic operation. That means refilling. The protocols and everything can run automatically. And with safety like hydrogen measurement and oxygen and the way around. Okay, then to the last topic, the analysis of environment catalyst layers. I want to show you mainly one method, is atomic force microscopy. I think most of you heard of it, but if not, still a small introduction. So you do force separation curves at, let's say, on 1 micrometer, 1024 or something like that, for separation curves. And at each point, then you get the phase shift, adhesion, stiffness, dissipation, deformation, and also electronic conductivity if you use electronically conductive AFM. So you with the AFM tip, then at point 2, there's like the snap. So you would the first contact of the surface, then you press until a maximum force. And when you retract, you can fit that curve and get the stiffness of the materials. So in that case, it's a standard sample with polystyrene, low density polyethylene, and showing the stiffness differences between these materials, and you get really nice contrast between these. At point 4 is the maximum negative force, and it's the adhesion. Also, this can be used to see different materials. And at point 5, you completely away from the surface and do this on the next. And AFM tips can have like a resolution of 1 nanometer. That's the best. Then you have like an AFM spike, or 25 nanometers when you have a platinum coating. Shown here is for proton exchange membrane electrolysis measurement, where you can see the height measurement, deformation, stiffness, used with 2 different solvents. And here on the upper one, the black one is the catalyst, and the right one is the ionomer. You can see that the distribution is here much worse compared to the second. Because here is much more accumulation visible. And as AFM does like quasi 3D measurements. You can overlay these structures here shown on the right, so the height, and overlay with deformation, modules, electronic conductivity. Yeah. Another example is shown here for a rhenium mixed oxide catalyst, where we developed that DLR. And at the beginning, the catalyst is completely covered with the ionomer. And after breaking procedure, the ionomer is not anymore completely covering the catalyst. And interestingly, after long-term operation, we saw this also in ion cut samples. The catalyst is really pressed into the membrane, but the performance was not much lower. Yeah, but HYScale also works very nicely for membranes, and here are two standard membranes. On the left side, you see here like quite large phases. This is the scale wise 200 nanometers. But the second image is higher performance, then has smaller phase or smaller phases, let's say like this. And this, the sample on the right side, I also want to show because this lamellar structure is quite nice for that very different functionalized cross-linked AM membranes. Okay. Like I said, if you're interested in mathematical samples, I'm interested. If a publication comes out, we can have a collaboration on that one. But also, we discussed before when we discussing test bench design and tech design. Can do that. Okay, and then thank you for your attention, and thank you for inviting me here.
Thank you.
And thank you, Daniel, for the laptop.
Thank you. Thank you.
Thank you, David, for the presentation. Very, very nice. I was wondering for the first configuration, where you put up a middle match with this flexible 1 km, and then they get felt.
Yes.
Have you tried? Just one. Have you tried with the liquid foam or?
Not on that configuration, but at DLR we also use the foam. Yeah. But as I know, it's not. I mean, you compress it once, then it's compressed.
Yes.
Yeah.
Because sometimes you work with the liquid pelt and sometimes with the liquid foam.
Yeah.
And I was wondering because of the, I don't know if you had any explanation, but you can also, let's say, try with liquid foam.
Yes. In yes. Yeah.
Sorry, don't do it. Okay. Thank you. Is there any other question? Yes, we have another question. Away from me. 1 second.
The data that you have shown for the configuration with the
For the internet, this was not the stack. It was single cell.
okay, but in the stack you do the dry.
We tried both.
Okay.
At the moment, I would say we are more in the tri-cathode.
Okay. And the pressure was 15 bar you applied on the.
This is our aim. We're not there yet.
Yeah. Thanks.
Because we optimize the design I have shown here. We still optimizing it a little bit more.
So at the moment, I would say that either pressurized on both sides or then maybe
no differential pressure.
Okay, no differential pressure.
Yeah. We have, let's say, tested up to 5 bars.
Right.
On our setup, and it's in our tested already higher, right?
Yeah.
Yeah.
And the electrolyte was 1 molar all the time.
0.1.
0.1. Thank you.
So I'll follow up. Thanks a lot for a great presentation regarding the committed mesh you're using. Have you tried as well like different expanded metal below it, like say different mesh width and heights, or for example, there's also some setups are using perforated plates to have it in between. Opinion on that? The meshes you use?
I mean, the expanded meshes, it's really a good idea to,
Wait, 1 second. Yes.
really good idea to try different ones, but in that project we were set to one. So not because of a partner, but because of time constraints. So.
But the knitted mesh were fixed, or how that idea?
No, this were not fixed. This came up to in different other projects also. Yeah.
Thank you.
But for expanded mesh, yeah, in other projects we tried also different ones, and these can have also great impact. But yeah, like I said, we have not the time to do all the different configurations.
I would leave the floor to the speaker for PROMISERS if they want to talk about highlights and key results.
Okay, so I will present some. Thank you for inviting us. I will present some results from the PROMISERS project. I'm Marcel Boerlichter, also from Leitat. And so the PROMISERS project is to develop new non-fluorinated components for fuel cell and electrolysis. So we have the project divided in two main streams, which is hydrocarbon-based and bio-based. So what we are doing, we are developing novel ionomers, and then from these ionomers, we are making membranes, and we also use them for the ink formulation. And then afterwards, we're going to the MEA assembly. This is all supported by simulation and also sustainability and safe by design. And then afterwards, we're going to the single cell, and then we go to a short stack using fuel cell and electrolyzers. And then also we have a look at upscale and market. So we are looking at ionomers for membranes and inks, also for non-fluorinated reinforcement for membranes. And also we are looking at non-toxic solvents to improve the safety and sustainability. Furthermore, also non-fluorinated ionomers in the catalyst and in the MEA, and validation, like I said, in the single cell and short stacks. So the first part is the hydrocarbon-based ionomers. So here we have two type of synthesis. We have the hydrocarbon-based synthesis done by HYScale, which you can see on the left. So here we have the PFAS reference, and then we have the first hydrocarbon-based ionomer, which you can see the IIC, the conductivity, and the E modulus. We also are IIT is making hyperbalanced PBI, which is excellent thermal and mechanical properties, and large number of thermal functional groups. So it's also quite interesting polymer for high temperature. So they synthesized the hyperbalanced PBI membranes. They used the linear PBI and the hyperbalanced PBI, and using mild polycondensation conditions and Eaton's reagents. And the membranes were prepared via solvent casting using 4 weight % of polymer. So here you can see some membrane samples, and they used phosphoric acid doping for the addition of mobile proton carrier. And so they have here 3 types of membrane. Where you can see the first one is the linear PBI membrane, and then we have a combination of the linear and hyperbalanced membranes. So you can see also that the membrane 3 is the best performing, so they successfully developed the PBI membranes, and small additions of hyperbalanced PBI enhances the phosphoric acid uptake and proton conductivities significantly. So this is the best results they obtained. So then we have the other parts, the hydrocarbon-based ionomers by HYScale. So they first started with small batches, so they want to have environmental sustainable alternative to fluorine-based membranes, and also lower cost and improve thermal and chemical stability. So we have small batches of these new polymers, which we then tested, which were sent to the partners. So different formulations were made, one in organic solvents, and also we made some dispersions, and from this organic solvent solutions and dispersions, membranes were made and they were tested. So at later we are working on the reinforcement of these membranes. So we do this with nanofiber reinforcement. So here you can see the equipment we are using. We have a roll nanofiber spinning equipment, which can be used for this also. You can see some samples above, and then we have several polymers we tested. This is polysulfone and polyamide. So we can also control the parameters of the nanofiber webs, and then we can use this as a reinforcement for the membranes. So we also apply some heat treatment to connect the fibers and have a more rigid reinforcement. So as we are using quite similar polymers as for the membranes, so if you use organic solvents, this polymers also dissolve in the organic solvent. So that's why we are looking also in different post-treatment strategies to have a reinforcement polymer that is not dissolving in the common used organic solvents. So we are using thermal treatment, we're using chemical cross-linking, and also looking at photo cross-linking and also cross-linkable polymers. So you can see here some at the lower part some cross-link, some thermal treatment of the nanofibers, and then on the right side you can see some ferrocraft alkylation of PSO, which was not going so well. As you can see, it's getting quite dark. But currently we are working on cross-linkable polymers to see if this can be improved. So if you look at the membranes which were made from the hydrocarbon-based polymers, they were verified against the Aquivion standard PFAS polymer. So here you can see the Aquivion reinforced polymer, which has the thickness, the ion exchange capacity, swelling, the lambda, Young modulus, tensile strength, etc. And the first hydrocarbon-based ionomer which was developed. So thicknesses are very similar. IEC is a little bit higher. Swelling was also reasonable, and then also the lambda was also, the hydration was also quite reasonable. And then we continue developing the second one, which you can see over here, which has some improved results compared to the hydrocarbon-based one. And then also we used the reinforcements, and as you can see here, we obtained quite some nice membrane with high ion exchange capacity. Swelling was reasonable. Dehydration was also within the targets, and then the conductivity was also within the targets. And also the strength of the membrane was also sufficient. But the next step will be optimizing this on a little bigger scale, and then prototyping for the short stacks and of fuel cells and electrolyzers. So we are doing the same for the bio-based route, which you can see here. Here also we have nanofiber reinforcements. So we were looking for reinforcement of bio-based, which you can hear cellulose triacetate and cellulose acetate. But we tested several more, also some bio-based reinforcements. And then for the membranes, this is based on the cellulose membrane formation process, where they used cellulose materials to make this membrane. So they used sulfur-ethylated CNF to make the membranes. So within the project, they one goal was to optimize or improve the IAC of these membranes, because they don't have a lot of these groups, sulfonic groups that can conduct. So we have done some sulfonation. So here we have the CNF, which was sulfonated using various routes, and then also the CNC, which was also sulfonated, as you can see here. So when you sulfonate cellulose materials, it's getting very viscous. So this is one of the main issues of cellulose materials, which you can see here. So that's why we're also coming to the next. So we also want to use this ionomers for the catalyst inks. So that's why we need a certain range of viscosity to apply this as an ink in the MEA. So here you can see several combinations we did with CNC and CNF, and also some speak was used. So various combinations, and then you can see the sulfur content, and then the IEC of the membrane. So we were able to obtain IEC over 1. So that was the primary goal. So as you can also see, the sulfonated CNC it has a higher IEC than the sulfonated CNF. So that's why we did a combination, and the combination of which was performing best was the 75% of CNC and 25% of CNF for the inks. So also the incorporation of speak enhances the IEC, which because speak also has sulfonated groups, and which enables us to operate at higher solid content, so to 8%. But if you then look at the ink formulation and MEA development, so the ionomers were provided to the NORA, which did some ink preparation, and also they did the PTL selection and procurement. So they tested several different PTLs, fiber felts and particles, and also woven and knitted. And then here in the bottom part, you can see the materials they used for the electrolyzer and for the fuel cell. So for the electrolyzer, they tested for the anode the Becker's material, and for the cathode PTL the ADV-Carb material, which is a carbon paper, and then for the fuel cell they used the same materials. So currently we are arriving to the MEA assembly. So we in the first part of the project we did the development of the materials, and now we are going to the MEA assembly, and this will be tested using operating techniques by IIT, and also supported by simulation from TNO using a numerical model to predict the water concentration, temperature, potential and pressure. And also we are keeping in mind the safe by design to use solvents that are not toxic, which can be scaled up. And then afterwards we are going to single cell testing and short stacks for fuel cell and electrolyzers. So that's from my side. Thank you very much. If there are any questions.
For the presentation, I was wondering about the glass membranes that you talked about, employing some reinforcement. And I was wondering, I think the last one you showed in the table is a reinforced one with 20 microns of thickness. And my question actually is, have you tried that one for both technologies? Like for the electrolyzer and also fuel cell?
Sorry, can you? I don't understand what's your question.
Okay. I was wondering when you were talking about the PEM membranes.
Yes.
for some of them, you show that you put a reinforcement inside.
Yes.
And I think the last, in the table, the last one, you put the membrane. It's a reinforced membrane of 21 microns, I think, of thickness.
Yes.
And I was wondering if you try that one for both technologies, for the electrolyzer and also for the fuel cell. Just as a question, a general question, because with employing an reinforcement changes a lot the performance if you are working with electrolyzer or with fuel cell. Just as a general question,
Yes. So we have not done any fuel cell or electrolyzer tests. So these are just membrane samples that are tested in the lab, looking at the properties of this type of membranes. So in principle, now
so
we are going. So now we are going to make this MEAS, and then we are going to test the single cell. So currently we have not tested any of these materials in single cell.
Okay, thank you. So you're more in the preliminary, let's say, characterization of the membranes, and then you're going to give it to the model. Okay.
Yes.
Thank you.
Okay,
Do you have a
just a question from my side. Unfortunately, we didn't see the ending part of the presentation, so maybe you showed it, maybe you didn't. My question is actually for the membranes. Have you maybe checked or did you show any result with regards to the permeation test, or maybe just via diffusion or something to see how these membranes or materials perform as a function of permeation?
Sorry, I didn't hear you very well. So can you repeat?
So my question is, have you tested these membranes as a function of the permeation test, or have you done any preliminary permeation test for these membranes?
No. So we did very standard test with the current membrane. So in plane conductivity, stability, and also mechanical stability of these membranes. So currently we don't have any data on permeation or.
Oh, okay.
Okay, thank you.
So, for the development, the idea behind the study that we are doing here is to improve the behavior of these membranes, but to balance the characteristics as transport stability, resistability, and stability with the major characteristics that produce without PFAS. So the building blocks of the process is about the meeting of the requirements for each for the membranes. There is the prediction of silane network into a polymeric phase, and also to improve the flammability, the detachability, and the reproducibility of the membranes themselves. So one of the most challenging topics that we are studying in our lab is about the design of the component of the membrane itself. So the point of view, we are working on inserting the backbone.
If you can move the microphone closer to you, because they cannot hear you. Maybe also the volume of the voice.
Perfect. So, as I said before, we are approaching the problem of the membranes by integrating a polymeric backbone to a silane network. So, The polymers, the role of the polymers is to provide a backbone and to improve the characteristics of the testability and the handling of the membranes during the separation phase. And also to introduce conductivity characteristics, science, and to increase the chemical and mechanical resistance. The approach to integrate silane networks is to add an inorganic scaffold that can build as lipid cohesion and dimension stability, and also improve the water resistance of the network. So we are also taking into consideration some silane, functionalized silane to modify the polarity balance and also to improve the interpartial compatibility and the morphology of the membranes. So the logic behind our development is divided in 3 major steps. So a formulation, a design of the formulation, and internal screening to evaluate the characteristic of the product that we are developing, and also the selection of more promising candidates for the functional characterization. So the things that we are taking into account in this developing are the filmability, the self-settling of the membranes, the water stability, the workability, the handling of the membranes itself, and also the reproducibility of the process of the deposition. Okay. So the approach that the thing that we now have produced for the project is that we had a target of 6 candidate target membrane target candidates. At this moment, we tested 9 different routes from for the formulation, and we sent 4 of these 9 to the functional characterization. So the thing that changes between all these types of membranes are the polymers that we use as a backbone, the different functionalized silane, the hydrophilic to hydrophobic balance. Also, we consider the different solvent route and different drying and post-treatment and also casting strategies. Okay. Some of these membranes are also feeding the development of the catalyst supporting layers. I don't know, Anto. Okay.
And as a part of Work Package 5, at FASTCH2ANGE, the idea is to evaluate the ionomers developed for new catalyst supporting layers for anode and also for the anodes. This way, the idea is to evaluate the compatibility of the components and, of course, make different compositions of the inks that varying the percentage of the ionomer, which solvents and which ratio of this solvent, and to proceed to CCMs, catalyst-coated membranes. And this way, our approach also is to do a semi-automated spray coating and also through a pilot line for automated CCMs. But the idea is to evaluate these PFAS-free ionomers developed and to assess finally the electrochemical properties of these CCMs.
Mentioned before, another topic that we are developing in the project is the substitution of with PFAS-free sealing components for gasket and seals. So in this case, the approach is to cast different materials in specific mold by using the soldier route to modify the chemistry of the materials. And yes, this is something related more to the results of these materials by analyzing the swelling, the solvent resistance, and the chemical resistance of these new materials, and yeah, to go on with the developing phase of the new materials. So I will leave the floor to Emmanuel. Yeah, if you want to, I can.
So maybe here, can you hear me?
Yes.
Okay, thank you. So within FASTCH2ANGE project, IDENER and VTT, we are in charge of the development of 3D multiphysics analysis to try to predict the behavior of this new of how these new materials, PFAS-free, affect to the electrochemical performance to the single cell. And right now in the screen, you can see some preliminary results about this simulation. In the left side, I just want to clarify that these results are made with PFAS-based material taken from the literature just to validate the simulation model. And here on the left, you can see the behavior of simulated system using the typical platinum and iridium catalyst with an Nafion commercial membrane. And we obtain a very reliable model that matches quite well with the results reported in the literature for this kind of materials in the electrochemical multiphysics modeling. And also with this model, we were able to simulate the fluidodynamic of the anode in this case, trying to predict the behavior of the formation of oxygen during the operational conditions. So all this data are being parameterized and will be used to also fit two AAA-based tools that will be used to show that from VTT side, we were also able to simulate the different geometrical conditions or how these geometrical conditions affect to mechanical properties as membrane stress with the compression force of the bolts and also distribution of these forces in the system. And also these parameters are being used to try to predict the behavior of these PFAS-free materials that will be incorporated in the future. And we will use it to train the AI models that are expected to be developed within the scope of the project. So that's all on my side. I give the word back to Alicia.
morning, everybody. This is Fabio. Yeah. I don't know if you can hear me. If you don't, stop me. This is Fabiola Brusciotti. I'm from Tecnalia, like Antonella, and another role that we have in FASTCH2ANGE is the development of PFAS-free GDL for the PEM electrolyzers. And here, although it's less crucial than in fuel cells, the PEM electrolyzer, the GDLs are usually covered with hydrophobic treatment based on Teflon, and that ensures effective water management, but it might reduce the porosity, altering the pore size distribution, or decrease the electrical conductivity by increasing the resistance. So what we are doing is substituting them, being careful that this is not happening. So we are doing this through, also in our case, through sol gel coatings. So we use a sol gel synthesis where we use different functional group in order to provide the required functionalities. Then it's the coating deposition we are doing now by dipping, but we want to try as well by spraying. And then just in the process, we cure the sample. And okay. Then here, is what we are doing, our process flow. So we do a sol gel synthesis, then we check that the solution looks uniform and there are no phase separation. If that is the case, we go to measure the viscosity with time in order to check the stability of the solution, and we apply to the GDL for the moment by dipping. And then we analyze the preliminary analysis, our visual appearance, thickness of the coating, then characterization with SEM, water contact angle, and interfacial contact resistance. In case this doesn't go well, one of these, or we consider that it needs optimization, that's where we are now. It's like we change reagent, we modify everything, and we go on again. And then the next step is to characterize them, let's say, in situ or within a cell. But that we are going to send now eventually the first samples, and then to scale up for further ambient characterization in change. Why? Okay, yes. Because, okay, this is just some preliminary results to show. So in terms of on the left, this doesn't look what? Yeah, on the left you can see the water contact angle. This is just of the glass substrate to check that our coating indeed hydrophobic, and indeed we reach more than 90 degrees. And then these are the blues are three commercial GDL coated with either with microspore layers, this one, or we coated with a Teflon. And then the green ones are our coating. So in all cases, you see that with two type of carbon papers, E20 and E35, we get hydrophobic conditions. In the case of the E35, the base carbon paper is completely hydrophobic, and we do see an increase. And then the coating thickness we check is around 100 to 200 nanometers. I'm not showing here the same results, but we saw that the coating is nicely distributed on all the fibers without clogging the pores. However, the fact that it is so nicely coated on the fibers, we see that the interfacial contact resistance is higher than in the benchmark. Here on the left, we see the commercial GDLs, some that with and without the Teflon, and then here one type of carbon paper with the Tecnalia coating, and depending on these are 4 types of coating for different conditions, and we see that it increased. So this moves too much. The one on the left, it's lower, so that's probably what we are going to go on with. And the case of the other GDLs is just too much. And then here, this is for the moment we just did on one of them. We wanted to see how the interfacial contact resistance changed with the pressure of the cell.
So, well, the pressure at which it's closed, I don't know how to say. So, and we are gonna do it with more of them in order to check how it changed, and then we pass them for more in situ analysis to really see the functioning and what we gain or not with this coating. And well, this is just what I just said. One result that I hadn't shown was the solve viscosity. Here, yes, we checked for now just for 2 weeks. So we have to produce now a new solution to check for a longer time. And well, the other results I just mentioned. And then besides sending for characterization more in situ, we want to well, use the type of carbon cloth to see if there is different on how it works on other type of more the carbon cloth with the carbon, carbon paper. This was carbon paper, and we want to try carbon cloth to see how it works with that, and then adjust more the formulation mostly to lower the resistance and optimize the application method, which might also affect how the coating distributed and give a lower again the resistance. And so this is one line, and that's it. I don't know.
Yeah,
what's more ahead. I don't know what it works better. Maybe,
yeah,
the mouse.
I think that's all for
Okay. Okay. Examination.
yeah, that's all for the results of the FASTCH2ANGE part.
Okay, so thank you, Alessia, Antonella, Fabiola, and Jose Manuel. And is there any question here or online for the FASTCH2ANGE project? And Matteo, sorry, I forgot to mention Matteo. Yeah, Marcel, yes.
Yes, one question. I saw that you are also developing new materials for membranes and new ionomers. Can you say a bit more on which types you are developing, or?
Okay, so the question is about the new materials for ionomers. Alessia, would you like to take this question?
Yeah, as I said, we are basically using the same material that we are using for the membranes, which is from the polymeric side, a combination of PVA and SPIC fundamentally, and also with the addition of silane to improve the hydrophobicity of the material. So it's basically the same mixture that we are using for membranes, and yeah, we're trying also for to be used for the catalyst layer. Yeah.
Okay. Yes. Thank you.
You're welcome.
So if there are no other questions, thank you again.